The main objective of this project was to build a single oscillator digital sound synthesizer with wireless note control using an Android phone via Bluetooth. The device was designed in modules, which we would test individually. Once each module was working correctly, we incrementally connected them together and ensured they were communicating as intended. On the hardware level, we had an amplifier, which was a standard resistor-controlled non-inverting amplifier, which was implemented with an LM386 operational amplifier. The circuit had a gain of 2. There was a gain control potentiometer before the input to the amplifier, which allowed us to have volume control. After the amplifier, there was a low-pass filter. This filter was a simple first-order RC circuit, and the cutoff was controlled by a potentiometer in the RC circuit. Next, we also had the wave selection button, which is a cyclic digital counter which toggles between the 4 waveforms. A photoresistor was used also to sense how bright the environment was and set the brightness of the LCD display accordingly. So bright spaces will have a dimmer screen and vice versa for darker places. There's an LCD display and an LED matrix. The LCD display is programmed to show the note, octave, volume and waveform type currently selected. When a waveform is selected, the LED matrix displays a moving representation of the shape of the wave. There's also Bluetooth communication. The Bluetooth USyd chip was paired with an Arduino phone running an app called Bluetooth Serial Controller. This app allowed for programming of the signals sent. Features we intended to include but didn't have time to were things like note hold, that is, a sound would only be played while pressing the button. Displaying the cutoff frequency of the low-pass filter on the LCD display. Also, an obvious thing is we did not have time to put this in a case, which would have been ideal.
During testing, we made frequent use of both an oscilloscope and a guitar tuning app called PitchLab Pro. Early stages of testing involved simply observing the output of the DAC on an oscilloscope and ensuring that it corresponded to the intended waveform. A constant frequency was set and a push button was used to cycle through each wave in the wavetable array. As we were using pre-written wavetables from a tutorial on Arduino.cc, this result was achieved without any complications. After implementing the Bluetooth note control, which used the equation shown on screen to calculate the frequency of each note in a given octave, the oscilloscope was used to measure the frequency of the signal and compare it with the expected value. For example, note A in octave 4 corresponds to 440 Hz. The oscilloscope also proved invaluable in verifying amplifier and low-pass filter functionality by measuring gain and observing the changing shape of the signal as the cutoff frequency was swept from minimum to maximum value. These clips demonstrate the gain range of the non-inverting amplifier on sine and triangle waves. At lower values, there is clearly flattening of the lower end of the wave due to DC offset. However, this was a compromise we were willing to make to avoid saturation at higher gain values. This is the effect of gradually decreasing the low-pass filter's cutoff frequency. Notice how as higher frequency sine waves in the Fourier series are being attenuated, the shape of the wave changes. Here you can see the frequency of a sine wave increasing in discrete values as we step through the chromatic scale across different octaves, and the corresponding note being displayed instantaneously on the LCD screen. The first problem we encountered was the time taken to execute the delay microseconds function, which we used to set the sample delay and in turn the frequency. This limited the maximum frequency playable by the synth to 120 Hz, which is a B note in the second octave and is barely audible. This was overcome by using timer interrupts, so whenever the timer counter 4 reached a certain value, which was determined by the input note, the current sample in the table was written to the DAC, the sample number was incremented, and the timer was reset. By programming the hardware directly, the frequency of the sound was much closer to what we intended. Another problem was setting a maximum gain for the op-amp chip that didn't result in saturation. This problem was rectified by selecting appropriately sized resistors for the non-inverting amplifier for a gain of 2. and placing a voltage divider after the DAC and before the potentiometer, which controls the gain. There were a couple of problems that couldn't be addressed in time. The first was the noise generated by the LM386 op-amp chip. This could have been mitigated by connecting a capacitor between the differential inputs. The second is that the more code we put in the loop, the more detuned the output was. We thought that by observing the detune on the tuner app, we would be able to include an offset in our frequency equation to account for the delay caused by the function calls. However, the detune was different depending on the note being played, and this problem was realized days before the due date, so we didn't have time to derive an equation for the offset. This problem wasn't rectified at all, and as a result our synth is quite detuned, particularly at high frequencies. All of the following clips show the previously outlined functionality, but with an 8 ohm speaker connected at the output instead of the oscilloscope.